This video is about limits. The technique of taking a limit of a function is used frequently in mathematics and physical sciences. We can use limits to give values to functions that are not technically defined at certain points, and the idea of a limit is the basis of differentiation and integration. We'll cover some notation, and then how we can take limits at a finite point and limits of a function at positive and negative infinity. The idea of a limit at a finite point is to take a function f of x and a point x0. We look at how the function behaves as we get close to x0, but not actually at x0. The function may or may not be defined at x0, but this does not necessarily affect the existence of a limit at x0. We can approach the point from the left and right, and as we get closer to x0, the value of a function will get closer to a fixed value. Here, as we get closer to 1.05, the function gets closer to 0.87, but this isn't the same as saying that the function is equal to 0.87 at 1.05. We're not looking at what happens at 1.05, but rather what happens as we get close to 1.05. Here's some handy notation. We can say that f of x tends to L as x tends to x0 using these arrows, or we can write that the limit of f of x as x tends to x0 is L. In this example, we're going to be looking at this function, e to the x minus 1 over x, and taking the limit of a function at x equals 0. Notice that this function is not technically defined at x equals 0, since we would be dividing by 0, but we can give it a value using limits. As we get closer to 0, the function gets closer to 1. So we can say that as x tends to 0, f of x tends to 1. Or using the other notation, we can say that the limit of a function as x tends to 0 is 1. If you want to see how we can show this more formally, it is included as a worked example on our webpage. In our second example, we're going to look at our limits at infinity. This essentially means that we're looking at what happens to the function as the input gets very large and positive, or very large and negative if we're looking at negative infinity. Let's look at the reciprocal function, 1 over x, and we'll take the limit as x tends to infinity. Here's the graph of a function. We can see that as x gets large and positive, 1 over x gets small and tends to 0. This is also the case as x gets large and negative. So we can write that as x tends to infinity, f of x tends to 0. Or using our alternative notation, the limit of f of x as x tends to infinity is 0. In this video, we've looked at notation for limits and some examples of how to find limits at both a finite point, positive infinity, and negative infinity. To conclude, the main reason we use limits is because they allow us to evaluate functions at points where they may not be defined by considering how the function behaves around that point. If you want some more worked examples, practice problems, or example applications, you can go to our section on limits of the Math Survival Skills webpage. Thanks for watching.